This conference will now be recorded.
So good morning, students. We will be starting from where we left off last class. We had discussed about electromagnetic radiation and the study of interaction of electromagnetic radiation with matter, which comprises uh, spectroscopy. So before we go into the various types of spectroscopy, we also saw about the electromagnetic spectrum and the various regions of the electromagnetic spectrum. These were the various regions as you see here on the screen: gamma rays, X-rays, UV, visible, infrared, microwave, and radio waves. So these were the different regions of the electromagnetic spectrum. We also, since the first chapter deals with UV visible, we have seen about the UV region being further divided into two uh, classes, that is vacuum UV and the UV. It's also called the far UV. The vacuum UV is called the far UV because it is further away from the visible region, and the UV region, which is the near UV, which is close to the visible region. Then you have the visible region, which extends roughly from 380 to 780 nanometers. So just after the UV region, we have the visible region. The visible region, of course, is made up of different colors. And finally, you have the infrared region after the visible region. So these were the colors that I told you. The color that is absorbed is the complementary of the color that is transmitted. And if you are trying to analyze a solution that is purple in color, you will be using the wavelength corresponding to green color, because that is the wavelength which will be absorbed. Green will be absorbed, not purple. So that was what we discussed last time. Here, what exactly you mean by complementary colors? If you arrange some of the colors in a circle, you get a color wheel, and then you can make out the complementary colors, that is the opposite colors. So colors directly opposite each other on the color wheel are said to be complementary colors. Blue and yellow are complementary colors. Red and cyan are complementary. So are green and magenta. These are also complementary colors. So mixing together two complementary colors, say yellow and blue, colors of light, will give you white light. This is not something like you mix two pigments, yellow and blue, because then you will get green pigment. This is not like that. What a mixture of colors will give you white light. What this means is that if a particular color is absorbed from white light, so white light has all the colors. If a particular color is absorbed, say yellow color is absorbed, what your eye detects by mixing up all the other wavelengths of light is its complementary color. You see blue. Actually, it is the resultant of the mixture of all the remaining colors. Because only yellow is absorbed, all the remaining colors mixed together will appear blue to you. So this is what we see. If you see a blue solution, then yellow light has been absorbed. I hope this is a little more clear than last class about complementary colors and how absorption occurs, how transmission, which color is transmitted. We also saw about the interaction of electromagnetic radiation with matter. This is what is study of this is spectroscopy. We have seen the four possibilities. You could have absorption occurring, you could have scattering or reflection occurring, you could have change in orientation or polarization, you could have the phenomenon of fluorescence or phosphorescence. So our first chapter actually deals with absorption spectroscopy. So this is the one we will be concentrating in the present chapter. Subsequently, you will also be studying about each of these. Scattering or reflection occurs when you have, say, biphasic or systems like suspensions, emulsions, where the radiation, when it falls on the suspended medium, it gets scattered or reflection depending upon the wavelength of radiation and the dimensions of the scattering particle. You could also have change in orientation of light if you have um, optically active compounds. So dextrorotatory or levorotatory compounds, then you could have change in orientation of light. This will be studying in the chapter of polarimetry, and sometimes after the phenomenon of absorption has occurred, you may see emission of light in the form of fluorescence or phosphorescence. So this also will be dealing in detail in the chapter of fluorimetry. So presently we'll be studying about absorption. So what does absorption mean? Absorption of electromagnetic radiation. So in spectroscopic nomenclature, what is the definition of absorption? A process in which a chemical species in a transparent medium selectively attenuates certain frequencies of electromagnetic radiation. Just in case somebody is not sure about what attenuates mean, it means decreases the intensity of. I hope you remember what is intensity of radiation. Intensity of radiation refers to number of photons being propagated in the beam. Okay, so attenuates means decreases the number of photons in the electromagnetic radiation. So it's a process in which a chemical species in a transparent medium. So your substance should be in a clear solution to measure the absorption. So when light passes through a clear solution containing a substance capable of absorbing that light, then you will see a decrease in the intensity of the electromagnetic radiation coming out of the solution. So now we'll try to understand absorption of radiation and when it happens, when it may not happen. According to quantum theory, every elementary particle has elementary particle could be an atom, molecule, electron, ion. Every elementary particle has a unique set of energy states, the lowest of which is the ground state. So according to the quantum theory, every elementary particle has a unique set of energy states, the lowest of which is the ground state. Absorption occurs only if the energy of photon matches exactly the energy difference between the ground state and one of the higher energy states of the particle. This is very important. When will absorption occur? You have to try and understand this. When will absorption occur? Absorption occurs only if, it is actually if and only if, the energy of the photon. Now, photons make up the electron beam. So, the energy of a photon matches exactly the energy difference between the ground state and one of the higher energy states of the particle. What is ground state? It is the lowest energy state and it will be the stable state of the molecule or the elementary particle. And any of the higher energy states, an energy state that is usually not occupied but and has higher value, that is a higher energy state. So exact difference between the two should be the energy possessed by the photon to ensure that absorption takes place. I'll show with energy level diagrams, which will make it a little more clear to you. In absorption spectroscopy, the energy carried by a photon is absorbed by the analyte, promoting the analyte from a lower energy state, that's the ground state, to a higher energy state, that's the excited state. So from the lower energy state is called the ground state, higher energy state is called the excited state. So when a molecule or an atom or an electron absorbs energy from a photon, the energy that is absorbed promotes the particle, elementary particle, to a higher energy state or to the excited state from the ground state. Absorbing a photon of UV or visible light causes a valence electron in the analyte to move to a higher energy level. So in case of UV visible light, because of the energy possessed by this light, it can cause a valence electron in the elementary particle or in the molecule to move to a higher energy state. So this is an energy level diagram showing absorption of a photon. So here you have E0. This is the lowest energy state. These are higher energy states, E1 and E2. So E2 value is higher than E1, which is higher than E0. Now the molecule is residing here, or since we are dealing with UV visible, we are concerned with valence electrons. The electrons are residing in the lowest energy state. Now, when a photon passes near the electron, the energy of the photon, or the photon, which is a packet of energy, that photon is absorbed by the electron in E0. How did it absorb? Because the energy of the photon is E1 minus E0, or it is equal to the difference between these two energy levels. If the energy of the photon equals E1 minus E0, then the electron will absorb that photon. When the electron absorbs the photon, it will undergo a transition from E0, lower energy state, ground state, to E1, which is the excited higher energy state. Similarly, you have another electron from the same molecule also, it can be another electron which is exposed to a photon having energy E2 minus EO. E2 minus E0. This photon has more energy than the one having energy equal to E1 minus E0. This photon also can be absorbed by the electrons from the same molecule, because there is one more energy state in this molecule, so called E2. So this electron, upon absorption of energy from a photon equal to E2 minus E0, will undergo a transition from the lower energy ground state E0 to the higher energy E2. So this is also absorption. In both the cases, upon absorption, we say the electrons have got excited. They have gone to the excited state. Now, they will not reside in the excited state too long, because in the excited state, the electrons are not stable. They are possessing more energy than they can possess. So it's a unstable state. Immediately they try to lose that energy and they try to come to the ground state again. That process would be called relaxation. So the intensity of photons passing through a sample containing the analyte is attenuated because of absorption. So what happens is these two photons in the beam were absorbed by electrons of the analyte. So suppose there were 10 photons in the beam, 2 of the photons have been absorbed. So what is getting transmitted out of the sample of analyte is only 8 photons, the remaining 8 photons. So there is a decrease in the number of photons entering and exiting. And that is why we say the intensity is now reduced. And this reduction or attenuation has happened because of absorption of photons by the analyte. The measurement of this attenuation gives absorbance. So absorbance is a measurement of the absorption of photons by the analyte. So this is an energy level diagram, another energy level diagram showing absorption of a photon. Now this is a more detailed way of showing it. You have E0, which I had shown earlier. This is the lowest energy electronic energy level. E1 is a higher electronic energy level. Now here what you see is, you also see a number of extra lines which have been called V1, V2, V3, V4. V0 coincides with E0. Whatever is the value of E0 is the value of V0. All these V's, these are vibrational levels within this electronic energy level. Similarly, you have about 5 vibrational levels in the electronic energy level E1. This V1 would have higher energy than this V1, just like E1 has higher energy than E0. So now we will see that what happens, what are all these? These are the transitions that take place. Their energy levels have well-defined values, that is, they are quantized. Each of these has a definite energy value. Absorption occurs only when the photon's energy, the photon that is incident on this analyte, it will get absorbed only when the photon's energy matches the difference in energy, that is delta E, between two energy levels. So what are the different types of energy levels that you will see? Now in case you can have this is a difference between two energy levels, this is also a difference, this is also a difference. So a photon that has energy equal to V1 minus V0 can be absorbed, V2 minus V0 can be absorbed, V3 minus V0 can be absorbed. A photon having this much energy, a higher energy, like V4 of E1 minus V0 of E0. This much difference, that is a much greater energy, will also get absorbed. So from this you can make out a particular analyte will not absorb only one energy photon. It can absorb energy, it can absorb photons of slightly different energies. So different energies can be absorbed by a photon. But what I would like to tell here is, suppose I will just draw here one. Suppose your photon has energy equal to this much. So here you see now the photon has so much energy. What is this energy? Difference between this is V1, V2 and half of it. So it is V1 and a half minus V0 of E0. If a photon is possessing so much energy and it is incident on this analyte, then that photon will not be absorbed, because this energy does not correspond to difference between any two energy levels in the molecule. I hope that makes it clear. There should be, in any molecule, there are a set of energy levels. And if the photon's energy matches exactly with the difference between any two quantized energy levels, then it will be absorbed. If a photon has so much energy, that is, it does not correspond to difference between any two quantized levels, then it will not get absorbed. I hope that is clear now about absorption. So we can represent absorption of radiation by equations. So absorption always resulting in excitation. We can give it like m plus h nu. What is h nu? It is the energy of the electromagnetic radiation. If you remember, E is equal to h nu, where h is Planck's constant, nu is the frequency of radiation, and E is the energy of the photon in the electromagnetic beam. So when photons are absorbed by the molecule, then the molecule undergoes a change and it is represented as M star. M star is the molecule now in the excited state. M star is not a stable molecule because it possesses more energy than it can normally do. And that's why M star immediately relaxes this or it undergoes the process of relaxation, and it gives back M, releasing some energy. So this is the process of relaxation which follows immediately after absorption. So when in this time, so it will be within 10 raised to minus 9 seconds. So within fractions of a second, that is. So within that time, this relaxation will occur. Now, relaxation process could occur in different ways. I've listed out three methods. First one is heat generation, second is photochemical decomposition, and third is fluorescence or phosphorescence. The first one, we will first look at that. Now, generally in UV visible spectroscopy, we use solutions, that too dilute solutions of the analyte. So you have the analyte molecules in the presence of large number of solvent molecules, because it's a dilute solution of the analyte in the solvent. So when this process of relaxation occurs, the energy that is given out is distributed to other molecules in solution. The other molecules predominantly are the solvent molecules because it's a dilute solution of the analyte. So these solvent molecules take up the excess energy, part of the excess energy, and therefore energy gets distributed in solution, which results in a very minute increase in temperature of the solution. This is the most common way of relaxation occurring in UV visible spectroscopy. Sometimes this may not occur, or what may occur is photochemical decomposition. That is, M star, when it has excess energy, and this excess energy could be used by M star to undergo decomposition process. That is, chemical decomposition of M may take place using that extra energy. If this occurs, then M will not be formed because M undergoes decomposition and a new substance is formed, say N is formed. So energy would be used up here to form N. That is photochemical decomposition. The third possibility is emission of fluorescence or phosphorescence. Now, M star may undergo relaxation, releasing the extra energy and giving back the molecule M. This extra energy could be released in the form of electromagnetic radiation. That is, in other words, we could say electromagnetic radiation or energy could be emitted from the molecule. So if this is emitted in the UV visible region, we call it UV visible fluorescence or phosphorescence. The difference between these two mainly is in the time taken for emission to occur. So these are the different ways in which relaxation can occur following absorption. So absorption is always followed by relaxation um, in spectroscopy. Now, once this whole process of absorption relaxation occurs, now how do we interpret it? For that, we will take the help of a spectrum. What is a spectrum? Before we go into absorption spectrum, what's a spectrum? It's a plot of some function of attenuation of a beam of radiation. versus the wavelength, frequency, or wave number. The vertical axis, so it's a plot, it's a graph. So the vertical axis will maybe either percentage transmittance, or it can be absorbance, or it could be log absorbance. The horizontal axis or the x-axis could be either wavelength, frequency, or wave number. Any of these are used on the x-axis. Now, the absorption spectrum is usually, that too in the UV visible region, is usually a plot of wavelength on the x-axis and absorbance on the y-axis. It is different for, say, IR absorption spectrum. In case of IR absorption spectrum, by convention, it is percentage transmittance on the y-axis versus wave number on the x-axis. So for different regions, we could use different terms on the x and the y-axis to construct an absorption spectrum. In UV visible region, it is usually, it's not wrong to have the others also, but it is usually absorbance on the y-axis versus wavelength on the x-axis. So measuring photons as a signal. Energy is transferred between a photon of electromagnetic radiation and the analyte. We have seen that that's what happens in absorption. From the photon, the energy is transferred to the analyte. And in relaxation, from the analyte, a photon of energy is released. So spectroscopy is divided into two broad classes: absorption spectroscopy and emission spectroscopy. Absorption spectroscopy basically deals with studying the absorption of a photon of energy by the analyte. Emission spectroscopy deals with the study of emission of energy in the form of photons from an analyte. So these two are different types of spectroscopic studies. Before we go into absorption spectroscopy, we will just look at the molecular orbital theory. What does this theory state? It states that electrons in atoms exist in atomic orbitals, while electrons in molecules exist in molecular orbitals. Okay? Electrons in atoms exist in atomic orbitals, while electrons in molecules exist in molecular orbitals. What is a bonding molecular orbital? A molecular orbital where electrons have a lower energy than they would in isolated atomic orbital. So a bonding orbital is a molecular orbital where electrons have lower energy than they would in isolated atomic orbital. Okay. What is antibonding molecular orbital? It's a molecular orbital in which electrons have a higher energy than they would in isolated atomic orbitals. So antibonding molecular orbitals, in other words, have higher energy than the bonding molecular orbitals. Bonding molecular orbitals are the ground state energy levels, and antibonding orbitals are the higher energy or excited states. So the ground state refers to the state of lowest energy. Electrons can be promoted from ground state to a higher excited state by input of energy. So ground state is the lowest energy state, and electrons in the ground state can take up energy and be promoted to higher excited energy state. So what's excited state? Any electronic state other than ground state, because it refers to higher energy state. The lowest energy state is the ground state. So any electronic state other than the ground state is the excited state. types of molecular energies. Rotational energy, this is one type. It is associated with the overall rotation of the molecule with atoms considered as fixed point masses. Imagine a molecule which has a number of atoms. So these atoms are considered to be fixed in the molecule, and the rotation of the whole molecule, when you consider that none of the atoms are moving, the rotation of the whole molecule, the energy associated with that is the rotational energy. This is relatively lesser energy. Next is vibrational energy. This is associated with the oscillation of atoms of the molecule, which are considered as point masses about equilibrium positions. So now you consider there is a molecule and there are atoms in the molecule. Now these atoms are considered to be point masses. They are not fixed point masses. Okay, so they are point masses and they can oscillate about their equilibrium positions. That is, they can move, say, to the left and then to the right, so they can vibrate. And the energy associated with this oscillation of atoms in a molecule is called vibrational energy. Vibrational energy, of course, is greater than the rotational energy. Then you have the electronic energy. This is associated with the motion of the electrons while considering the nuclei of atoms of a molecule as fixed points. So here we are going still further inside the molecule. You have the atoms, and within the atoms there's a nucleus and circulating electrons. These electrons of atoms, they move to higher energy levels, and that or the energy possessed by these electrons and their movement to higher energy levels, the energy associated with that is called the electronic energy. When you are considering that the electrons are moving to higher energy levels, we consider the nucleus of the atom to be a fixed point. Okay, considering the nucleus to be fixed, the electrons are moving to higher energy levels. That energy associated with such a motion of the electrons is called electronic energy, which is greater than vibrational and rotational energies. So molecular absorption brings about changes in energy levels, and these changes in energy levels are called transitions. Transitions are of three types. So changes in energy levels are generally referred to by the word transition in spectroscopy. And transitions could be of three types. You could have rotational transitions, you could have vibrational rotational transitions, or you could have electronic transitions. So we will see each one of these in detail. Thus, each molecular energy state is comprised of an electronic, vibrational, and rotational component, such that E total, that is the total energy possessed by the molecule, equals E translational plus E internal energy. So what is internal energy of the molecule? Internal energy, E equals E electronic, that is electronic energy, plus vibrational energy plus rotational energy. So the sum of electronic, vibrational and rotational energy gives you the internal energy possessed by the molecule. This is energy in addition to the translational energy possessed by the molecule. Now, comparing the electronic, vibrational, and rotational, as I mentioned in the last slide, the electronic energy possessed by the molecule would be greater than the vibrational energy, which is greater than the rotational energy. So, the least energy is the rotational energy. Now you have energy level diagrams, with the help of which I hope it will become very clear to you what are these transitions. Now you can see these energy levels that we have drawn. This is the energy axis, so it increases in this order. That means E0 is lesser than E1, which is lesser than E2. Okay. Now you also see in molecular absorption what happens. You have been here you can see the word IR, visible, and UV. So this type of transitions under IR. So this type of transitions are seen in IR region or by absorption of IR photons. These type of transitions are seen in the visible region or absorption of visible photons results in this type of transitions. And absorption of UV photons will result in this type of transitions. Just uh, to help you recollect, UV radiations have got greater energy than visible radiation, which has greater energy than IR radiation. So what about the wavelengths? The wavelength of UV radiation is smaller or shorter than the wavelength of visible radiation, which is shorter than the wavelength of IR radiation. So out of the three radiations, IR has the longest wavelength. Now here you see there are photons with particular energy corresponding to wavelengths lambda 1 to lambda 4. This is lambda 1, this is lambda 2, this is lambda 3, lambda 4. So these are the wavelengths of radiation which are incident on a molecule. These radiations of these wavelengths correspond to certain energies. So the photons have different energies. It could have this energy or this energy or this or this. So all these 0, 1, 2, 3, 4, they correspond to vibrational levels. So here you can see IR radiations. These are the IR radiations, lambda 1 to lambda 4. They can only bring about vibrational transitions. They cannot bring about electronic transitions, which indicates from transition from this E0 to E1. Minimum is this. So much energy is not possessed by IR photons, and therefore IR photons can only bring about vibrational rotational transitions. If you see this, lambda 1 dash to lambda 5 dash. So lambda 1 dash, lambda 2 dash, 3, 4, 5 dash. These are different wavelengths with slightly differing energies. All these energies of the photons correspond to the difference between any two energy levels in this molecule, so they can be absorbed. So all these wavelengths are shorter compared to lambda 1 to lambda 4. These are the longer wavelengths, these are shorter than these, and therefore the energy possessed is more. They bring about electronic transitions. So this brings about an electronic transition from E0 to E1. Lambda 2 dash brings about an electronic transition from E0 to E1 1. Lambda 3 dash brings about electronic transition from E0 0 to E1 2, this one. So each of these, however, is possible, and this will give rise to a visible spectrum. If you go to still higher energy or still shorter wavelengths, that is lambda 1 double dash to lambda 5 double dash, lambda 1 double dash, lambda 2 double dash, and so on. These are much higher energy photons. These photons are also capable of being absorbed by the same molecule because there is one more electronic energy state in this molecule, that is E2. And lambda 1 double dash brings about a transition from E0 0 to E2 0, lowest vibrational level of excited electronic state E0. Whereas lambda 2 double dash brings about a transition from E00 to to 1. Okay, so all these are also possible, and these are much higher energy transitions, and they occur in the UV region, giving rise to UV absorption spectrum. That's how various absorptions occur in molecules. Now, relaxation process, because this immediately will be followed by relaxation. Once the electron reaches this position, it is not going to be stable, so immediately it will try to relax. So there could be vibrational relaxations, so relaxations which do not give any radiation. Those are always represented by wavy arrows. You can see all this. These are non-radiative relaxations. So you see wavy arrows all over here. This is a wavy arrow from 4 vibrational level to 3, from 3 to 2, 2 to 1. That is, there is a decrease in energy. But here it is small energy releases, and these are called the vibrational relaxations. Now you come to this. Once it reaches E2, then this electron may undergo a further relaxation. This is also non-radiative. So it could be something like heat generation. So it could release the energy due to collisions. So various types of those external conversion methods, it could release the energy. So, but no radiation is emitted. And that's why you see a wavy arrow. It comes to E1 electronic state. Again, it will undergo vibrational relaxations, come to the lowest vibrational level of E1. And then again, by collisional deactivation or external conversion, it could come down to E0, and further vibrational relaxations, the molecule may come down to the ground state. So here you have, this is the energy axis. This is a colored representative of the same thing, but what I have indicated here is the spectrum, how it is observed. So this is absorption. So here absorption is occurring, and you get the absorption spectrum. This is a different set of wavelengths, and this is a set of wavelengths. So when this is absorbed, it goes to S2 excited state, from S0 the ground state, and gives rise to a band. When this is absorbed, that is lower energy blue colored radiation, then you get another absorption peak. This, on the other hand, represents fluorescence, because S1 is a singlet state. We'll study that in the fluidimetry chapter. So this is due to the emission that is taking place due to transition from the excited state to the ground state. So here you get a band. And this is phosphorescence, which takes place after a time delay due to something called an intersystem crossing to the triplet state, from which again further you have vibrational relaxation, phosphorescence greater than 10 raised to minus 3 seconds. So it's a delayed process. This takes more time, this little less, still lesser, and this is the least.